Well, aloha everyone, and welcome back to Human Nutrition here at Chaminade University. Today we will be discussing Unit 5, which is lipids, fats, oils, and waxes. We'll be talking about what a lipid is and how lipids differ in their different structures and how lipids are digested, absorbed, and transported throughout the body. We'll talk about the functions of lipids within the body, and then of course the dietary recommendations for all of the different types of lipids, including total fats, fatty acids, cholesterol, and trans fats. We'll talk about good, bad, best, worst, alternative food options for different types of fats, including things like essential fatty acids, saturated fats, and again, trans fats. And then we'll talk about fats and their role in the development of heart disease, such as atherosclerosis, and we'll explain how different lifestyle choices can affect your risk of heart disease. So let's get started. So what are lipids and how do they differ in their structures? So lipids are an entire category of biomolecules that's going to include things like triglycerides, phospholipids, and sterols. So here on the right we have triglycerides, and here we have a glycerol head and 3 fatty acid tails, right? Triglycerides. And then we also have phospholipids. Phospholipids we will talk about extensively when we talk about cell plasma membranes. They're comprised of a polar head here and a non-polar tail. So that's going to be an amphipathic molecule, and they're going to orient themselves such that all of the polar heads are going to align and all of the non-polar tails are going to dangle this direction, and we'll orient them in a plasma membrane such as a double lipid bilayer. So we'll have 2 layers of heads with tails dangling inward. That's going to create a lipid bilayer, which will end up separating out the internal and the external aqueous solutions of the cell. Lipids are going to contain carbon, oxygen, and hydrogen as their main atoms, and generally they're hydrophobic. What does that mean? That means that they don't dissolve in water. The exception, of course, would be this phospholipid, which would not dissolve in water per se, but does have a polar head that would interact well with aqueous solution. Now, the fact that they are hydrophobic means that they tend to clump together in aqueous solution. And we'll talk about all of these different phospholipids in just a second. So lipids provide many functions within the body. The first and foremost, they're energy storage and provision. They also provide insulation, if you think of like blubber on a whale, for example, or fats on mammals. And they also manufacture things like steroids and bile. They're going to play an essential role in transporting nutrients that are fat soluble into the blood supply, and they're used to manufacture key sex hormones and are the major component of cellular membranes, which I just mentioned previously. Now, the building blocks of triglycerides and phospholipids are fatty acids. Now, fatty acids are basically a long chain of carbon with hydrogen atoms on either side. So here's where carbons are allowed to make 4 bonds. So I'm going to start with the middle carbons first. This carbon is going to be bound to 1 carbon on either side. So you can picture this like a long chain of carbons that are holding hands. And each carbon also is able to make 2 more connections, right? If it's already made 1 to each of the carbons on either side, that's 2. There's 2 left. And they do that by adding hydrogen atoms above and below. So as you can picture, this is going to be considered a saturated fatty acid in that all of the carbons are single bound to the carbons next to them and maximized in the amount of hydrogens that they're able to bond. On the end here, we have a carboxylic acid group, COOH, with a double bond to the O, and we have a methyl group on the other side, or CH3. Now, when we talked about using biomolecules for energy, it was noted previously that fat has a really high amount of kilocalories, and that's because it has a higher ratio of carbon and hydrogen to oxygen. So as we saw previously, carbohydrates and proteins were approximately 4 kcals per gram, whereas fats are 9 kcals per gram. And there's many different types of fatty acids, and the way that they differ are going to depend on a couple of things. First and foremost, the length of the carbon chain, and then also that degree of saturation. So when I said something was completely saturated or unsaturated, that's basically talking about, let me go backwards just one, it's talking about the amount of connections that it's making to the other carbons. If it's making 1 connection to each carbon on either side, and there's no double bonds anywhere, then it's completely saturated. But if somewhere you see a double bond between 2 carbons, then it's going to be an unsaturated fatty acid. And that's going to determine the shape, because every time that we have a double bond, and we have that unsaturated fatty acid, then we can have a kink in the tail. Now, The length of fatty acids is approximately 2 to 80 carbon long, but most of them are going to be between 12 and 24 carbons. Short chain fatty acids are anything that's under 4 carbons, medium would be 6 to 10, and long would be 12 or more. Now, long chain fatty acids are the most common that you're going to see in your food, and they're going to take a little bit longer to digest than short or medium chain. As you can imagine, you'd have to break 12 down into smaller and smaller components to get to the medium, so long chain fatty acids can break down into medium, which can break down into short. Now, as I mentioned, fatty acids are going to have multiple different characteristics. So they can vary by length, i.e., how many carbon molecules are there, right? This acetic acid here only has 4 carbons. And as you can see, it's going to be completely saturated in that every carbon is bound to 1 carbon on either side, and we are maximizing the amount of bonds that we've made with our hydrogen atoms. This is palmitic acid. It's also a saturated fatty acid, right? That carbon chain is never disrupted by a double bond. Here's oleic acid. Oleic acid does have 1 double bond in the middle, so that's going to be a unsaturated fatty acid. In fact, this would be considered a monounsaturated fatty acid because it has 1 site that has a double bond. This one would be considered a di or a polyunsaturated fatty acid because it has 2 or more kinks in the tail where we have double bonded carbons to one another. All right, and the degree of saturation of the fatty acid is primarily determined by how the carbons are held together. Namely, are they held together by all single bonds, or are there some double bonds in there as well? And in a saturated fatty acid, all of the carbons are going to be bound singly to the carbons on either side and maximizing the amount of hydrogens that they're bound to. That means they're going to have 2 hydrogens each in that middle part of the chain. There's no double bonds found anywhere, and these guys are going to be a little bit more solid at room temperature and have a higher melting point. So it's going to be things like your bacon grease or your butter, for example. Now, unsaturated fatty acids have a double bond somewhere along that carbon chain. So instead of binding to hydrogen, they're going to have a double bond between 2 carbons. And if we have one of these double bonds, it's considered monounsaturated. And if we have 2 or more, it's considered di or polyunsaturated. And these guys tend to be liquid at room temperature and have a lower melting point. Think like your olive oils, etc. And this example I like to give is akin to having paper clips that are lying flat and paper clips that have been all bent out of shape. So you can fit more flat paper clips in a box. That would be the saturated fatty acids. Now, saturated fatty acids, because they're all single bond carbons, they have no kinks in those tails. But the unsaturated fatty acids have bends in them, kinks, right? This is akin to the bent paper clips. And you can fit a lot less bent paper clips into a box than you could the ones that are going to be perfectly formed and flat. And so those saturated fatty acids can take the form of something like butter or, like I said, bacon grease, something where we can compact them very thickly, and therefore they tend to be solid at room temperature. Whereas the unsaturated, we can't fit as many in, and that makes them appear to be liquid at room temperature. Now, the fats can spoil through a process called oxidation, and oxidation happens basically when we have an oxygen molecule that comes in and takes the place of a hydrogen molecule. So spoiling of fats through oxidation is called rancidity. Now, anytime we have a double bond, it's a little bit less stable than those single bonds. So if you have an unsaturated fat in your food, it's going to be more susceptible to rancidity, so it's going to become rancid more quickly than foods that are entirely saturated with saturated fats. And this is just the process of oxidation. So basically a hydrogen is going to end up coming off. That would be this one here. A hydrogen molecule ends up coming off and an oxygen ends up taking its place. And this hydrogen is more susceptible than, say, this hydrogen, because this hydrogen is next to a double bonded carbon. And so these 2 would be most susceptible, or these 4, I suppose, would be most susceptible to what's called rancidity, or again, spoiling of your fat through an oxidative process. Now, this is something that is kind of the bane of the manufactured food product world. So manufacturers try to enhance the stability of these fatty acids and reduce the rancidity by doing several things. The first, they add antioxidants. And secondarily, they package the food with low exposure to oxygen. So either vacuum sealing it, or they'll seal it with air, but that air won't be oxygen. It will be comprised of other gases. You're also limiting the exposure to heat, right? Keeping things cool and light. You'll notice things come in dark boxes sometimes, or in dark packaging. And also they do what's called hydrogenation. And what is that? That means they're actually adding hydrogens to it to help stave off the oxidative process, right? If there's more hydrogens available in the packaging, then that hydrogen is more likely to take the place of the hydrogen that was lost than, say, the oxygen molecule, which again is what we're trying to avoid. Now, The first double bond that we encounter when we start from the methyl end, which is called the omega end, of unsaturated fatty acids is going to affect the property. So depending on where the first double bond is, we can have different properties of those fatty acids. And I'm not going to quiz you on this, but just an example, omega-3 and omega-6 fatty acids differ in the fact that the first double bond in the omega-3 is found between the third and fourth carbons, whereas the first double bond between omega-6 is found between the sixth and the seventh carbons. Now, anytime we have an unsaturated fatty acid, remember that happens because we have a double bond between two carbons. Instead of having these carbons are all going to be bound to, it's not depicted here, but each one of these is going to have a hydrogen that's going to complete its ability to bind 4 atoms. And if the hydrogens that dangle off of the double bonded carbons are on the same side, that's considered a cis unsaturated fatty acid, whereas a trans fat or a trans fatty acid would be if we have the hydrogens dangling on opposite sides of that double bonded carbon. And these are actually going to be considered pretty, I don't want to say dangerous, but they're a health hazard. And so that's why you see them listed in your fats on your FDA label. Here's a triglyceride. Again, the glyceride is going to have the glycerol backbone and 3 fatty acids. In this type, we've put together palmitic, oleic, and stearic. And that's going to be able to create, again, a triglyceride fats. The creation of putting the glycerol backbone together with those 3 fatty acids also is going to be a dehydration synthesis reaction, which means that we're going to be creating water at each of our bonds. So we have water that was created here, here, and here, resulting in 3 water molecules. And that's what it looks like if we do it up close. Here we have palmitic acid. This is going to have entirely saturated. This is a mono-unsaturated, the oleic acid, and again, a saturated for stearic acid. That's an example of a triglyceride. Now, triglycerides are the most common lipid found in the body. It's about 95% of the lipids that we eat in our foods. Again, it has 3 fatty acids and a glycerol backbone. And we have these in our foods for several reasons. One, it adds texture to our baked goods. It also is going to help make our meats feel tender, help us preserve freshness. And in our bodies, it's going to be stored as adipose tissue, which we can use or utilize for as an energy resource or an energy storage. Now, phospholipids differ from triglycerides in a couple major ways. First of all, they do have that glycerol backbone, but instead of 3, they now have 2 fatty acids, and they have a phosphate group as well as nitrogen-containing compounds. Additionally, they're what's called amphipathic, and amphipathic means that one end is going to be hydrophilic or water-loving, and one end is hydrophobic or water-fearing. And that means that the 2 ends of the molecule are going to interact with their outside environment differently. And in this way, we have them oriented together by multiple of these molecules. We can make a phospholipid bilayer of the cell membrane. Now again, I'm never going to quiz you on the actual chemical composition, but just to kind of show you here, we have the glycerol with a phosphate group combining with 2 fatty acids to make a phospholipid, which has 2 major regions. The polar head, which again is going to be glycerol, phosphate, and choline. That's hydrophilic. It's going to interact well with aqueous environment. So this is going to be oriented either towards the extracellular fluid, or if you were to picture that we take this entire thing and double it, so we flip it and we put 2 tails and another head, and then this side would be interacting with the cytoplasm. So in this way we can form a barrier between the inside and the outside of the cell. We can also use these phospholipids to be able to make what's called a micelle. So this is an example of a micelle. Basically, if we have a fat globule and we can orient all of these phospholipids such that, and picture this is 3-dimensional, so this is a cross section, but it's also going to have the heads sticking out towards you and sticking backwards. But we have the tails oriented such that they're able to surround the fat droplet. And in this way, this fat droplet can become what we call emulsified. Emulsified means when we're able to put fats into aqueous solution. And something that's an emulsifying agent is amphipathic, meaning it has one part that's hydrophilic and one part that's hydrophobic. And in this way, we're able to take the fat globules and surround them with these tails, but then have the heads interacting with aqueous solution. So that's what an emulsifier is. And we also are able to find these phospholipids in our cell membrane. So sterols are another type of lipids. The sterols are a little bit more complex than what we saw with triglycerides. You're going to have connecting rings of carbon and hydrogen. We have 4 rings that are connected together. These guys do not provide any energy, and they don't contain the glycerol or the fatty acids like we saw previously. The most common sterol that you would know of would be cholesterol, right? Cholesterol, and it's found in every cell in the body. It's going to be embedded in the cell membrane and has multiple different processes, or helps with multiple different processes of the body. It's a precursor to multiple different biomolecules, including vitamin D and your sex steroids, as well as your adrenal corticoids. Now, plants also have sterols. The major plant sterols are going to be phytosterols and phytostanols. here's what the structure of a sterol looks like. And again, I'm not going to quiz you on this, but just so you're aware, if you were to see something that has 4 carbon-backed rings, we have basically going to have 3 hexamers and a pentamer, and then some sort of reactive group dangling off. You can pretty much assume that that's going to be a sterol molecule. Now, so we talked about what lipids are. Let's talk about how lipids are utilized by the body. How are they digested? How are they absorbed across the intestinal wall? How are they transported throughout the body to whatever site they're going to be delivered? Now, lipids that come in from foods primarily come in the form of those triglycerides that we talked about, right? A glycerol head with the 3 fatty acid tails. To a lesser extent, we also are going to encounter phospholipids, again, from cell membranes, and sterols. And during the process of that digestion, we can take these fatty acids and make a combination of things. We can have free fatty acids that have been broken off, and then glycerol, and then monoglycerides. So there's a combination of these things that are going to be created from the breakdown of fatty acids. Now, just like any form of digestion, we have specialty enzymes that are utilized to break down lipids, and those are called lipases. So anytime you see lipase, you know you're dealing with an enzyme that breaks down lipids. And that starts in the mouth. The very first beginning of digestion occurs with lingual lipase, which is going to come in your saliva, so during the process of what's called mastication or chewing. And lingual lipase serves to hydrolyze or break down medium chain fatty acids into smaller chain fatty acids. After this, the bolus of food is going to travel through the esophagus into the stomach. In the stomach, we do have a lipase. It's a gastric lipase. Gastric lipase is going to come from the gastric juices, which are released from gastric pits. So this is going to actually break down 1 fatty acid off of a triglyceride. So if you picture the triglyceride was a glycerol head with 3 fatty acid tails, now it's going to be 1 free fatty acid and then a diglyceride, right? The glycerol head with 2 fatty acid tails. So we're basically breaking down triglycerides into diglycerides in the stomach. So here we're just showing you the organs of the GI tract and their role in the digestion of lipids. So the salivary glands are going to produce salivary lipase, right? The stomach is going to produce gastric lipase. And that's going to be able to access the fats by the fact that we have what's called peristalsis, or churning of this bolus of food. So it's going to be able to interact with these different lipases. After it leaves the stomach, it enters into the small intestines, where bile, which comes from the gallbladder, remember it's going to be stored in the gallbladder, but produced by the liver. And it comes out of the gallbladder and into the small intestines. That comes through the common bile duct and again into the duodenum, which is the early part of the small intestines. And that is going to result in the emulsification of fats into smaller and smaller fat globules. Right? Again, pancreatic lipase is going to be part of what comes through that bile, and it's going to hydrolyze or break down triglycerides into monoglycerides. So basically we're going to have this glycerol with 3 fatty acids, and now it's going to be broken down into a glycerol with 1 fatty acid, right, a monoglyceride, and 2 free fatty acids in solution. Additionally, something called phospholipase, which as you might imagine, hydrolyzes or breaks down phospholipids, is going to take this phospholipid here and then take 1 of the fatty acid tails off of it. The products of the hydrolysis of lipids are then going to be packaged into micelles, and I talked about those previously. They're little amphipathic style molecules that are going to surround fat globules to make this 3-dimensional structure, and that's going to allow them to be transported across the intestinal wall via enterocytes. Right? Then they're going to be absorbed and then be broken down into their component parts, right? And then short chain fatty acids are going to enter the bloodstream directly, whereas long chain fatty acids are going to have to, long chain fatty acids as well as cholesterol, phospholipids, etc., are going to have to be repackaged into what's called chylomicrons, and then they're going to be transported through the lymphatic system. So the lymphatic system is going to serve to pick up large lipid molecules and help get them back eventually into circulation. Okay, so again, how are we digesting these triglycerides? So first we have to break them down and then absorb them. So the fat globules in chyme tend to cluster together, and so they're going to have to be broken down and what's called emulsified. So we're going to take the larger fat droplets and break them down into smaller fat droplets. And in this way, we are going to allow lipase, again, it comes from the pancreatic bile, which comes through the gallbladder. It comes from pancreatic lipase, which comes from the pancreas. We also are going to have bile that comes from the gallbladder. I spoke too quickly. That's going to help and digest things in the small intestines. Now, pancreatic lipase is going to serve to digest the lipids. And again, it's going to result in a complex called a micelle. And micelles are responsible for transporting that lipid complex across the small intestinal wall where it can be picked up on the other side. Now, there's a hormone known as cholecystokinin, or CCK, and it's going to be a hormone that's responsible for stimulating the gallbladder in order to release the bile acid. Okay, so bile acid, remember, that's what's responsible for emulsifying the larger fat droplets into smaller fat droplets so that pancreatic lipase can break those lipids down. And again, it's going to be under control of CCK. And CCK is going to be released when lipids are present. So phospholipids, again, these are going to be the lipids that are going to help surround the cell and make the cell membrane. They're going to be emulsified by bile. Again, the bile is going to come from the gallbladder, from the liver originally, during digestion. And then they're broken down into the phospholipid remnant and two free fatty acids and eventually packaged into those micelles to be transported through the intestinal wall. Now, sterols are not digested at all. They're carried directly by micelles. They're small enough that they don't need to be broken down further, and they're absorbed intact through the intestinal wall. And they're emulsified, like many other things, by bile. Now, sometimes lipids remain undigested and therefore unabsorbed in the small intestines, and so they're going to enter into the large intestines where they bind with fiber and are then eliminated through fecal waste. Okay, so let's look at the role of bile in emulsifying fat. So again, the bile is going to be coming from the gallbladder, stored in the gallbladder but created in the liver. And the fat globules are going to be what's called emulsified or broken down into smaller fat globules by these bile salts. So the bile salts are going to surround these small pieces of the fat globules, make them smaller and smaller, allowing pancreatic lipase, again coming from the pancreas, to help break down the triglycerides into two fatty acids and a monoglyceride, which are then going to get picked up by micelles, formed into a micelle structure, and then get absorbed as micelles into the enterocyte, which is what's going to line the intestinal lining, and then go across this intestinal cell membrane to be picked up by either the bloodstream or by the lymphatic tissue. All right, so lipids are going to be picked up or absorbed based on their structure. Smaller things like glycerol and short to medium chain fatty acids are going to be absorbed directly into the bloodstream, but larger things are going to have to get picked up through the lymphatic fluid. And before they do that, they're going to combine with phospholipids to form what's called chylomicrons. And again, chylomicrons are very large. In fact, they're too large to be absorbed directly into the bloodstream, so they have to travel through the lymphatic fluid first, and then they're going to exit out of the lymph and eventually get into the bloodstream via the thoracic duct, which is next to the heart. However, as they travel through the bloodstream, they're going to be hydrolyzed or broken down, and the triglycerides inside the chylomicrons are going to be broken down by lipoprotein lipase, or LPL. And that's going to happen as they travel to the liver through the bloodstream, so they're going to get smaller and smaller until they finally are going to enter into the thoracic duct near the heart. So this is a cross-section of a chylomicron. So inside we have that fat droplet with triglycerides. Again, those triglycerides are going to get broken down piece by piece by piece by lipoprotein lipase as they have already gotten into the system. They get broken down eventually, but in the meanwhile, they're going to be carried by these phospholipids, which are going to surround in a micellular structure. Inside here, we're also going to have some proteins available, and cholesterol, as I mentioned, is also going to embed right into that leaflet of these phospholipids. So again, how are they going to get absorbed? So here's the inside of the lumen of the small intestines. They're going to get picked up, so micelles are going to get picked up directly, and either, depending on what they are, if they're carrying medium and short chain fatty acids, they're going to go directly into portal circulation and head to the liver. If they're going to need to be broken down a little bit more, things like phospholipids, free fatty acids, monoglycerides, etc., they're all going to get packaged into chylomicrons. And chylomicrons are going to be bigger than micelles, and they are going to skip the bloodstream and get picked up by the lymphatic system in the lacteal. So we have 4 lipoproteins that are responsible for carrying lipids in the circulatory system, including chylomicrons, which we mentioned, very low-density lipoproteins, low-density lipoproteins, and high-density lipoproteins. And basically these are going to be getting smaller and smaller as we head through these layers. So VLDLs, LDLs, and HDLs are all globular molecules. They have a lipid center and a plasma membrane around them. And the density determines function. So the higher density, the more protein, the less fat. So as we travel through, we're going to be taking our fats and breaking them down so that what's left over is the protein. So what does that look like? Okay, again, we're going to start with chylomicrons. And then we're going to make VLDLs from those. Again, VLDLs are much smaller than chylomicrons. And what's missing, not missing, broken down, is going to be the triglycerides. So the triglycerides are going to get broken down, creating the VLDL. More triglycerides get broken down, creating the LDL. And eventually we end up with HDL. And again, this is going to show you the triglyceride component. That's shown in that nice light yellow. The protein component shown in purple. We're getting more and more protein as we go, 2 to 10 to 25 to 50. The phospholipids, percentage that's going to be the phospholipids, and the phospholipids are on the outside, right? So we're going to be still have the same amount of those, but we're going to get less and less of the triglycerides, which means we're ending up with a higher percentage of the phospholipids. And then last is going to be the cholesterol. And as you notice, the LDL has the highest amount of cholesterol, and as we get back to HDL, we're going to lose it again. So LDL and HDL are considered your lousy cholesterol and your happy cholesterol, right? So it's a ratio of your LDL and your HDL in your body when they take your cholesterol levels. That's what's more important than your total number of cholesterol. All right, so let's talk about how we're transferring from this chylomicron to a VLDL. So VLDL are going to be comprised of these transport triglycerides, are going to have the role of transporting triglycerides and cholesterol from the liver to the cells. And this lipoprotein lipase is found on the outside of adipocytes, or fat cells, and muscle cells as well. And their objective is to cleave the fatty acids off of these triglycerides. And then the fatty acids move into the adipose cell and into muscle cells and are either stored for later use or broken down for energy. And that's going to increase the ratio of proteins to lipids because we're losing lipids as we're moving along. This process is going to take a VLDL and convert it to an LDL. So very low density to low density. And why are we increasing in density? Because we're losing our fat and increase our protein. All right, so when we talk about cholesterol, we talk about two different cholesterol numbers. One is LDL and one is HDL. Now, LDLs are involved in carrying cholesterol from the liver to the tissue, so they're the ones that deposit the cholesterol in the tissues. And HDL is going to pick up the cholesterol from the cells or the tissues and transport it back to the liver. So it's a ratio of the LDL to the HDL, how much is getting carried to the tissues versus how much is getting carried back to the liver. So typically you want to have higher HDL levels and lower LDL levels. All right, so this is just showing you again the different levels of these organization of the fat as it's being transported. So the chylomicrons are the largest version. These are going to be picked up directly by the enterocytes. They're going to end up going through the blood vessels via the lymphatic system. So first it goes to the lymphatic tissue, then it ends up in the blood vessels. As it travels through the blood vessels, fatty acids are going to get cleaved off. And again, that's going to happen by lipases on the outside of the muscle cells and the adipose tissue. And as those get cleaved off, the chylomicron remnant is going to get converted into VLDLs by the liver. Once it gets converted to VLDL, now we're going to have more fatty acids broken off. More of that's going to happen by muscle cells and adipose cells, etc. We have lipases. Eventually that VLDL becomes an LDL. We've lost a lot of the fat, and now we're going to have the remaining protein. Now LDLs are going to have a lot of cholesterol left, as I mentioned previously, right? LDLs have the highest amount of cholesterol, right? We've gotten rid of the fats one piece at a time, and now what's left? Mainly cholesterol and those phospholipids. So the cholesterol is going to be broken down and released to the cells, and then eventually the LDL will head back to the liver to get converted to HDL. And HDLs, again, produced by the liver, circulate in the blood and pick up the cholesterol from the cells and bring it back to the liver for elimination. These are going to be the very smallest, the highest in density, the highest in protein, and they have very little in terms of the cholesterol levels. I guess they still have more cholesterol than, say, VLDLs or the chylomicrons, but we've dropped off a lot of our, we've reduced a lot of the cholesterol that's present. Remember, LDL is delivering the cholesterol to the tissues. HDL is picking up the cholesterol from the tissues and delivering it to the liver. Okay, so what are the functions of lipids within the body? Well, lipids serve multiple critical roles in the body, including energy resources, structures of the cell membranes. the regulation of metabolism, the absorption or enhancing the absorption of fat-soluble vitamins. Remember, fat-soluble vitamins aren't going to be able to get into the bloodstream by themselves. You're going to need some sort of lipid carrier molecule. And providing a layer of insulation, such as blubber, in mammals to help regulate body temperature. Additionally, it helps serve to cushion the major organs so that they don't end up injured as they move along one another. Now, as I mentioned, fats provide a very high or highly concentrated source of kcals per gram, over 9 kilocalories per gram of fat. And that's going to be a resource that's readily available for the body when it needs energy. It's going to be one of the main sources of energy throughout the day, and anything that we don't use is going to get stored. Now, the body has an unusual ability. It has the unlimited ability to store excess energy as fat. So we're never going to say, oh, there's too much in our reserves. We've got plenty of fat to live for the rest of our lives. So what happens is the fat cells, which are very unique in that they're able to expand up to 1,000 times their original size, and then eventually once they hit that 1,000-fold threshold, they're going to divide such that the new cells are able to then create these much larger cells as well. Sometimes fat is stored in muscle cells, but most fat is stored in adipocytes or in adipose tissue. And this is what adipocytes or fat tissue looks like. These fat tissue can get very, very, very large. However, once we shrink down and lose that, we're never going to lose the cells. So even the cells get smaller, if we've already divided and divided and divided, we're still going to have excessive fat tissue. Again, here's an adipocyte. The adipocyte's going to be fed by fatty acids, glycerols, and triglycerides that are coming from those chylomicrons. Now again, fats are a very powerful energy source. It's going to actually be the preferred energy source by the heart and the liver and your resting muscle. So not muscle during exercise, but just general resting muscle. And this is going to allow the body to spare glucose so that glucose can be used in areas that really only rely on glucose, such as the central nervous system and your red blood cells, and provides a backup source of energy between meals. However, excess body fat is not what's actually used during prolonged starvation because we need glucose to metabolize fat. So although the glycerol portion of fat can make small amounts of glucose, which can then help break down fat, it's going to be insufficient to be able to induce the metabolism of fat for long periods of time. So during excess starvation time frames, if you don't have enough of sugar available, you're never going to be able to break down the fat to be able to access it. So we have several essential nutrients that are going to require dietary fat for absorption. Things like fat-soluble vitamins, carotenoids, cholesterol, phospholipids, etc. And so we need a minimum of 20 grams per day in order to stimulate the chylomicrons that are going to transport fat-soluble vitamins. We can also find fat in our sub-Q tissue as a mechanism of insulating our body to maintain body temperature. And again, as I mentioned, it helps protect your vital organs and your bones from trauma or tissue damage. However, if we have too much fat stored in our body, that can be very deleterious to the organism. It can be detrimental for the individual for multiple reasons, including risk of diabetes, heart disease, and hypertension or high blood pressure. Now we have essential fatty acids and non-essential fatty acids. Now our essential fatty acids are going to manufacture ecosinoids and cell membranes. Things like linoleic acid, which is converted into ALA or it's converted into arachidonic acid. And we also have alpha linoleic acid or ALA, which is converted into EPA, which then gets elongated into DHA. Again, I'm not going to ask you for any of these pathways, but I want you to understand that we have different types of fatty acids that play different roles within the body. Now, EPA, again, that comes from ALA, and arachidonic acid, which comes from LA, can make what's called ecosinoids. And ecosinoids are similar to hormones, but not quite hormones. So they're hormone-adjacent substances, and they regulate things in your body like blood clotting, immune system, and inflammation, as well as your blood pressure. We also need ALA or alpha-linoleic acid to help make healthy cell membranes, particularly in certain regions like nerve tissue and retinal tissue. Okay, so linoleic acid and alpha-linoleic acid both are able to make molecules downstream. So linoleic acid makes arachidonic acid, again, alpha-linoleic acid or ALA makes EPA. EPA can make DHA, which makes cell membranes, or it can make ecosinoids, same as arachidonic acid. Now these ecosinoids, again, as I mentioned, are going to be used to help regulate things like blood clotting, immune system, inflammation, blood pressure, etc. And then this DHA is used to create or incorporate into cell membranes. So what else do we use cholesterol for? So cholesterol is used as a building block for multiple different biomolecules, including hormones, like sex hormones, estrogen and testosterone, including bile acid, and also vitamin D. So you can see cholesterol here, as you can see the 3 hexamers and a pentamer, looks very similar to oleic acid, which is a bile acid. All we've done basically is we've removed this functional group and we've added a COOH group. Now, as I previously mentioned, phospholipids are the main component of cell membranes. Here's what I was talking about when I said we have a double layer. It's called a bilayer. Here we have the heads and the tails, right? The heads are going to interact well with an aqueous solution, in this case the outside of the cell, so this is going to be extracellular fluid. Then we have one set of tails and another set of tails and then another layer of heads. In this way, we're going to be able to interact well with the watery cytoplasm and the extracellular fluid, but provide a lipid barrier. This is a selective semi-permeable barrier, by the way, in which we're able to allow things to transport inside to outside and outside to inside. Inside this membrane, we also have cholesterol embedded to allow extra stability and fluidity to the cell. Now, how much intake should you be doing on a daily basis of things like triglycerides and cholesterol? Now, although the average American's fat intake is within the guidelines, which is approximately 32% of your total daily kilocalorie intake, but the type of fat consumed must also be considered. So while 20 to 35% of your daily kilocalories should come from fat, you have to pay attention to which fats you are eating. And excess fat consumption itself doesn't necessarily lead to weight gain, because just like we've discussed several times, it really is kcals in, kcals out. However, if you have a diet high in fat, more than likely you're meeting your daily kcals because fat contains concentrated kilocalories. So a diet high in fat is more likely to result in excessive kilocalorie intake than a diet high in the other food groups, or the other, biomolecules. We also know that fat is directly linked to heart health. So in order to maintain an adequate heart health, you should try to make sure that you consume less than 10% of your total kcals from saturated fat, and that you replace your saturated fats with monounsaturated and polyunsaturated fats. And we also want to limit our trans fats. Remember, our trans fats are unsaturated, but they're going to have the dangling of the H groups on either side of that bond on opposite sides. So they're going to emulate a saturated fat in that they're able to compact more tightly. The essential fatty acids include linoleic acid, alpha-linoleic acid, and we want to make sure that approximately 5 to 10% of our kcal intake comes from linoleic acid, and at least 0.5% to 1.5% of our total kcal intake comes from alpha-linoleic acid. So this is something that people often take with exogenous supplements. And if you already have heart disease, you want to really pay attention to the levels of these, as well as consuming essential fatty acids every day, so a gram of each, and consuming 2 to 4 grams of EPA and DHA, which we know is able to reduce your blood triglycerides. Currently, Americans are only going to be consuming about 0.1 to 0.2 grams. So that's probably 20 and change fold, 20 to 40 fold the amount that Americans normally consume. Okay, so what are not essential? So cholesterol, phospholipids, these are not essential because we're able to manufacture them by the body. So the liver is responsible for synthesizing cholesterol. It makes approximately 900 milligrams per day, and it's going to decrease the amount that it creates based on your dietary intake. So if we eat some, we need to make less. And we use a feedback system to monitor the total cholesterol levels in the blood. And objectively, we would like to reduce the risk of cardiovascular disease by limiting the dietary cholesterol. And if we can keep our dietary cholesterol underneath approximately 300 milligrams per day, we might be able to stave off cardiovascular disease. Now, dietary phospholipids include something called lecithin. And lecithin is a very common dietary phospholipid, so something that you eat. And the liver makes all of the phospholipids, including lecithin, that the body needs, and then it's digested by the GI tract, and so it doesn't enter the small intestinal cell intact. It's going to get broken down in the GI tract. So if we eat this lecithin, then we're going to have it broken down prior to digestion across the prior to absorption across the small intestinal cell, I apologize. Now, there are some supplement companies that claim that lecithin offers health benefits, but we don't have any data to support this. Some of the claims include things like weight loss and fat metabolism, cardiovascular health, and exercise performance. But as with all of these claims, they usually show someone who is also undergoing diet and exercise. And so it's not just the supplement that they're adding, but they're also saying used along with regular diet and exercise, which we know by itself can help with things like weight loss, fat metabolism, and cardiovascular health. So it's tricky when they say make those sorts of claims. Now, in order to replace your saturated fats, or at least reduce the amount of saturated fats that you're consuming in your diet, you want to try to replace them with unsaturated fats. So you want to consume more of the following foods, like vegetable oils, soybean oils, corn oils, canola oils. You want to eat more soybeans, walnuts, flax seeds, wheat germ, etc. If you want to increase your omega-3 fatty acids, like alpha-linoleic acid, you want to increase the consumption of walnuts, flax seeds, and canola oil, and eat more fatty fish such as salmon, tuna, and mackerel. Now, the previous wisdom was that you should eat a ton of cod liver oil. However, cod liver oil is very high in vitamin A, so individuals who already have regular amounts of vitamin A can end up in vitamin A toxicity. So you want to make sure that you avoid cod liver oil as it already has more vitamin A in it, so that can be detrimental if you end up with high levels of vitamin A. This diagram shows you the food sources of your essential fatty acids, such as linoleic acid and alpha-linoleic acid. And as I mentioned previously, you're going to want to try to eat things like flax seeds and soybeans, almonds, walnuts. And in your oils family, you want to have more canola oil and soybean oil, etc. This is going to show you food sources of those omega-3 fatty acids, so things like cod and tuna and crab and shrimp. Also sardines, you're seeing a lot of fish oils, right? Salmon, herring, mackerel. So this is where we're going to get most of our omega-3 fatty acids are going to come from fish products. Now, while it's the objective to decrease your saturated fat from your diet, it's almost impossible to eliminate all of your saturated fat. Some of your primary saturated food sources include things like animal foods, right? Cuts of meat that are fatty, milk products that are whole milk, skin on the poultry, etc., including plant sources like coconut, palm, and palm kernel oils. So it's very difficult to entirely eliminate all saturated fat from your diet. But tips for lowering your saturated fat include obviously limiting your intake of foods rich in saturated fat and consuming lower fat versions of the same foods, the fat-containing foods, and make sure that you read your nutrition facts panel to help you determine which foods are going to be lower in fats and which kinds of fats you're consuming. In order to help reduce the foods that contain trans fat and cholesterol, we want to try to make sure that, again, that you're monitoring what you are eating. Now, saturated fats from animal and plant sources are often used in home cooking and commercial food preparation. Why? Well, it does a couple of things. One, it decreases rancidity. Right? Additionally, it's going to help provide texture to baked goods. And as we've mentioned previously, texture is a very important part of what you eat. People have taste aversions based on textures. Even though they might like the way it tastes, if they have an issue with the texture, they're unlikely to eat it. Later on, saturated fats were actually going to be replaced, or more likely to use things like hydrogenated oils and trans fats because they perform a very similar function in terms of the texture and reduction of rancidity, but they don't add cholesterol to the diets. Okay, so what is hydrogenation? You've heard of partially hydrogenated or hydrogenated, etc. What does that mean? Basically, what happens when you hydrogenate a fat is you're going to be replacing saturated fat with hydrogenated fat. And what is hydrogenation? Basically, you're taking your double bonds and you're reconfiguring them. So you're going to take that cis fatty acid, which, as I mentioned, has one hanging left and one hanging right on the opposite side of that double bond, one hydrogen on one opposite sides. And in a trans fatty acid, we're going to have a more stable form where we're going to have the trans are going to be on the same side. Now, trans fats can be naturally occurring, but we also add trans fats. And we've demonstrated, or research has demonstrated, that trans fat is actually worse for heart health than saturated fats, even though they're unsaturated. They've been shown to raise your LDL and lower your HDL, which is the opposite of what you want. Obviously, you want higher HDL and lower LDL. And for this reason, the FDA has recently required that all trans fat be listed on the food label. So you want to try to minimize the amount of trans fats that you're eating in your diet. So here it shows you where the labels are going to show you your total fats, saturated fats, and trans fats. Now remember, trans fats are unsaturated fats, but they're going to mimic saturated fats in how they compact, and they actually have been proven to be worse for you, or at least equivalently bad for you, as saturated fats. So what you'd like to try to do is use liquid fats over solid fats almost all the time you eat and cook, right? The more liquid the fat is, the less saturated fat and less trans fat that it contains. Now, we consume a lot of cholesterol, and most of our dietary cholesterol comes from from animal products, but some does come from plant products. The cholesterol that's produced in plant cells is so minimal that they're generally going to be considered cholesterol-free. Now, we do have phytosterols and phytostanols, and these are going to be biomolecules that help lower the LDLs in our body by competing with cholesterol for absorption. They're found in things like soybean oil, fruits, vegetables, sesame seeds, legumes, cereals, nuts, and other plant foods. And oftentimes it's used as fortification. So food manufacturers fortify foods with phytosterols and stanols to help lower cholesterol in the diet. Now, Americans are becoming more conscious of their diet. Over 160 million Americans, which is about 80% of the adult population, was shown to intentionally choose lower fat foods and beverages. And when they were asked why during the survey, health concerns were cited as a major reason. Now, lower fat foods often contain fat substitutes. Now, fat substitutes give the same texture, so they have the same creamy properties of fat, but they will have fewer calories and less total fat grams. Now, there are three major categories of fat substitutes. They're either going to be carbohydrate-based, protein-based, or fat-based. The majority of fat substitutes are carbohydrate-based, and they use a polysaccharide from plants to help retain moisture and provide that fat-like texture that we like so much. We also have protein-based fat substitutes. It's going to be created from proteins, eggs, and milk, and again, it provides that creamy-like texture. You'll notice this texture is really the underlying theme here. And fat-based fat substitutes are fats that are actually fats but have been modified to provide the physical attributes, which is again texture, taste, etc., but less calories than regular fat, or actually interfere with the absorption of fat. So fat that we're unable to actually digest or absorb. Now, just like I mentioned that eating all fat won't make you gain weight, eating no fat won't make you lose weight, because overconsumption of kcals from anything, even if it's regular, low-fat, or fat-free products, can lead to weight gain, because really, overall, it comes down to kcals in, kcals out. This is showing you the different fat substitutes. Again, some of them are carbohydrate-based, some are protein-based, and some are fat-based. And the properties all have to do with texture, thickening, water retention, thickening, mouthfeel, moisture retention, mouthfeel, right? So all of these are going to help replace fats in your diet without you necessarily noticing, because you're still getting the same texture and mouthfeel that you would from fats. Now, fats have been linked to cardiovascular disease. So what is cardiovascular disease? So cardiovascular disease is an entire range of disorders of the vascular system, including disorders of the heart. And heart disease specifically is the #1 killer of adults here in the United States, and typically it begins with atherosclerosis. So what is atherosclerosis? Atherosclerosis is when we have fat and cholesterol that start off accumulating in the arteries. They get kind of lodged on the inside. They form plaques and lesions, and eventually blood flow is going to be impeded. And when blood flow is impeded, you get less oxygen and nutrients. Less oxygen and nutrients to the heart is going to result in chest pain, which is sometimes a precursor to an actual heart attack. Again, atherosclerosis is basically going to be when we have clogging in the arteries. It's going to start from the arterial walls and work its way in, and depending on where it happens, it can lead to a heart attack or a stroke. If the atherosclerosis is going to happen in the arteries leading to the brain, it can cause a stroke. Now, how does it progress? Typically what happens is we're going to have a slight injury to the lining of the arteries, which is going to cause an inflammatory response. When this inflammation happens, things like LDLs and other lipids are going to accumulate at that region of injury, and they become oxidized. And this is going to happen because they react with free radicals and metal ions, and this is going to result in macrophages extravating from the extravating means migrating out of the blood vessels. So they're going to be attracted to the oxidized LDLs, and then they form plaques. And once those plaques start, now this is going to be over time. So here's our healthy artery, and then we end up with an arterial injury. When we get arterial injury, we're going to end up with the accumulation of lipids. As lipids accumulate, we're going to end up with a long fatty streak, and as you see, it's going to get thicker and thicker and form an occlusion, where eventually only a small amount of blood is going to be able to get through compared to the healthy artery. So here's a healthy artery, and here's an occluded artery that has a plaque on a cross section. And as you can see, the actual area through which the blood can flow is drastically impeded. Now, there are several risk factors for heart disease, some of which are completely uncontrollable, some of them are controllable, and some we don't quite know yet exactly how they are going to play a role in heart disease. Some of the uncontrollable risk factors, of course, are your age, your gender, your family history, and whether or not you have diabetes or diabetic condition as a diabetes type 1. Controllable risk factors include diabetes type 2, which is later adult onset diabetes, and also high blood pressure, smoking, physical activity, excess body weight, and your cholesterol levels. All of these are things that you're able to control through diet and exercise, right? Basic nutrition. And there's some other risk factors, include your levels of C-reactive protein and homocysteine, as well as the presence of chlamydia, for example. And this would be something that would be controllable. Obviously, you could take an antibiotic and kill these guys off. But if we have chlamydia in the bloodstream, we know that that actually is also related to heart disease. Additional emerging risk factors include concentrations of LPA and the presence or absence of metabolic syndromes. Now, to lower your risk of heart disease, you want to try to make sure that you're lowering your blood lipids. Your primary risk factor is the concentration of lipids in the blood. So most adults starting at age 20 are supposed to have a lipid analysis profile done every 5 years, where they look at your cholesterol levels, they look at total, your LDL, and your HDL. So that's going to be used to calculate a risk score. And the risk score is going to be looking again at the total. If it's lower than 200, that's going to be good. If it's over 240, that's considered high. For LDL, if it's less than 100, that's considered optimal. If we're at 190 or above, that's very high. And again, that's a ratio of LDL to HDL. HDL was considered desirable to have over 60, and less than 40 would be considered low. So anyway, they use that to create a risk assessment to see where you as the individual stand in terms of the risk of developing heart disease later on in the future. If you want to try to have adequate heart health, you want to try to consume less saturated and trans fats, and also moderate the amount of cholesterol that you're intaking in your body. Your diets that are high in saturated fats are going to increase LDLs, whereas high cholesterol diets don't affect LDLs. However, you want to make sure that your saturated fats are going to be monitored. So the type of saturated fats that you're consuming might have a different impact on LDL levels in the blood. For example, myristic and palmitic acids are going to raise LDLs, whereas stearic acids don't raise LDLs. But because it's really difficult to isolate the foods by the types of saturated fatty acids they contain, the overall recommendation is just to lower your saturated fatty acid intake. As I mentioned previously, trans fats, although they are unsaturated, they also are going to act as saturated fats because of the way that they compact, and they are going to raise LDLs and blood triglycerides and lower your HDLs. All of these are obviously the opposite of what you want. So how else do we remain healthy? Try to eat 2 servings of fatty fish per week. These are going to be really high in omega-3 fatty acids. And as always, try to choose baked, broiled, or poached over fried. Limit the consumption of EPA and DHA to approximately 3 grams or less per day, which can help increase the risk of excessive bleeding and raise your blood glucose and LDL levels. So if you want to make sure that you are going to be safer, you want to have lower levels of these, which will obviously stave off the risk for excessive bleeding and lower your blood glucose and LDL levels. You want to intake less than 3 grams. And it occurs only with supplement. I'm sorry, if you intake more than 3 grams, it's pretty much only going to happen by supplementation. So oftentimes people are going to take these by taking exogenous sources of it. Omega-3 fatty acid supplements should be taken by with medical supervision, so you should make sure that you discuss this with your doctor in advance just to make sure that you aren't going to have any secondary byproducts of this metabolism. And pregnant women and children should consume approximately 12 or less ounces of fatty fish per week. So while everyone should be eating about 7 ounces, there's no cap for the other categories, but for pregnant women and children, there is a cap of about 12 ounces of fatty fish weekly. Now you want to make sure you're consuming more plant foods, which are going to be things like canola oil, soy, flax seeds, and walnuts. These are all rich in ALA. And choosing plant foods that are rich in soluble fiber. And trying to consume at least 2 grams of plant sterols a day, which are shown to lower your LDL levels by 10%. And plants that are foods that's rich in plant sterols include things like soybean oil, fruits, vegetables, legumes, nuts, and other plant foods. as well as margarine that's made with plant sterols, obviously. Antioxidants and phytochemicals are also going to be important. These guys neutralize your free radicals and help stimulate your immune system. This is going to result in a reduction in heart disease risk. These antioxidants and phytochemicals include things like vitamin E, vitamin C, beta carotene, garlic, flavonoids, and nuts. Additionally, I know we've all heard this multiple times, get in your exercise, keep your weight down, and quit smoking yesterday. Exercise is going to raise your HDL and lower your LDL, all good, and reduces high blood pressure and insulin resistance. All of this is beneficial to the individual. So you want to aim for approximately 30 minutes or more of what's considered moderate exercise a day. Quit smoking ASAP if you haven't done so already. Smoking is known to damage the walls of your arteries and accelerate the rate of atherosclerotic lesions. So the plaques build up faster for individuals who are smoking because smoking damages the walls. And smokers, even former smokers, are 3 times more likely to have a heart attack than non-smokers simply because of the fact that the smoking is going to damage the arterial walls and initiate or trigger the creation of these atherosclerotic lesions. So to decrease your excess LDL, there's a couple of things, dietary and lifestyle changes. So on lifestyle changes, as always, exercise, watch your weight. Dietary consumption, make sure you consume less saturated and trans fats, consume less dietary cholesterol, consume more plant-based and soluble fiber-rich foods. Now, alcohol has been shown in moderate amounts to reduce the risk of heart disease, and this is mainly in middle-aged adults. It's going to help increase your HDL levels and decrease blood clotting. Now, moderate amounts of alcohol are defined as 1 serving of alcohol per day for females, so 1 glass of red wine, for example, or 2 servings of alcohol per day for males. Thank you so very much for listening to me today. I really appreciate your time. So aloha, happy studying, and I will see you guys next time.